Okay, this is just a video on some Cartesian vector stuff. So starting with scalar multiplication. Okay, so wait, before I start. This is all going to be about C2, and it's all about Cartesian or algebraic vectors. So this whole topic is all on C2. Okay, so we're going to talk about scalar multiplication. So you know how we have vector quantities and scalar quantities? Okay, so vectors we represent, as we know, with a letter and then a little arrow on top. And then a scalar, we're going to use the letter K to represent that. So you can multiply a vector by a scalar. And here's what could happen. So if you had this vector, let's call this vector V, and you wanted to make it bigger maybe, you can multiply that vector by 2. So all that changes is its magnitude. So vector 2v would look like a vector that's just like vector v, but twice as long. So a scalar just changes the magnitude of the vector, not the direction, which makes sense since scalar quantities don't have a direction. Okay, I kind of lied because it could change the direction to the opposite direction. So if I wanted to say like negative 0.5v, I can make a vector that's, since it's negative, it would be going in the opposite direction as vector v, and it would just be half as long. So that's called scalar multiplication. So you can multiply any vector by that. So let's just take a Cartesian vector. Like, let's just say we had vector A, and let's say vector A was 3, 2. We can multiply this vector by a scalar. So let's say I wanted to find out what 2A is. Then that means I just multiply each component of my vector. So my new vector would become vector 6, 4. So it's now twice as long. Okay, and then that brings us into another word that we haven't used yet called collinear. So we learned about equal vectors, opposite vectors, parallel vectors, and there's something called collinear vectors. And I'm bringing this up now because collinear vectors are scalar multiples of each other. So here's what we know about collinear vectors. They lie on a straight line when arranged tail to tail. So if you arrange the vectors tail to tail, then they would lie on a straight line. Lie on a straight line. They're scalar multiples of each other. Scalar multiples of each other. So if we had a vector like 3, 2, and then we multiplied that vector by 2 like we did in the above question, 6, 4, those two vectors would be collinear. So if you were to plot them out, we had the vector 3, 2 would look like this, and then the vector 6, 4 would look like this. So these are collinear vectors. So another thing we know about collinear vectors is that they must be parallel. That makes sense, right? They're lying in the same line together. Okay, so that's what a collinear vector is. Okay, next thing we could say. So just another thing about scalar multiplication. So here's some properties of scalar multiplication. So it doesn't really matter. Well, actually, okay, so properties of scalar multiplication. So you know the distributive property that you learned back in grade 9? It works for scalar multiplication too, which I kind of just showed above. So if you had a scalar k, and then you had a couple of vectors that were being added together maybe, you can actually use the distributive property, and you can apply that scalar after you add the two vectors together, or you can apply the scalar before before you add the two vectors together. So you can distribute the scalar amongst the two vectors, or you can add the two vectors first. So that's a property of scalar multiplication. And then there's the associative property, which just means if you have a couple of scalar quantities multiplied together and multiplied by a vector, so if you have these three things, it doesn't matter what order you do them in. So it can be done like this also. Okay, sorry, moving on. I have a bunch of stuff I want to go over in this video, so I'm not going to spend too much time on each thing. Okay, next thing. Oh, this was just some terminology. It's not really a big deal, but just talking about Cartesian vectors. So let's just make ourselves a little grid here. I'm not really worried about the terminology too much, but just wanted to give you a visual that sometimes your textbooks uses, I noticed. If you have a vector like QR, for example, so we call this a Cartesian vector, and we would call it vector QR. So that would be a Cartesian or algebraic vector. Now, if we want to translate QR over to the origin and put it here, I personally would still call this a Cartesian vector, but you could give it a more specific name, and that could be a position vector. And often they represent a position vector at the origin, so we call it O, and then at some point P. And point P would just be like some random XY point. And then we would say, like, say we called this vector U, and we would say it's at that XY point. But yeah, sometimes that's called a position vector. So it's positioned right at the origin. So we could call it like vector OP. So you just might see that in the textbook a lot, where it refers to a point, and then it will refer to the vector as like O and then that point. So that's just saying that the vector is starting at the origin. Okay, so that's just like a random terminology thing, and just something I noticed that the textbook that you have does. Okay, next topic, unit vectors. It's a kind of important thing that comes up. So sometimes it's nice if we can represent Cartesian vectors with these unit vectors. They're kind of like the building blocks for Cartesian vectors. And I feel like they're represented in different ways. So sometimes I see them as like I and J with arrows, but I've also, like, the way I used to do it is with I hat and J hat. So I don't really care what notation you use. It's completely up to you. As long, just stay consistent. Pick one. Okay. Okay, sorry. Okay, so anyways, unit vectors. A key thing about unit vectors is that they have a magnitude of 1. Every unit vector has to have a magnitude of 1. And they have their tails at the origin. Tails at the origin. So for example, if you wanted to say the unit vector I, so this represents our x component, so it would be at 1 on the x-axis, and this would be I hat, and vector j would be on the y-axis at positive 1. Call that j, and we would represent them like I hat would equal 1, 0, and j hat would equal 0, 1. And these are just like, they're just exactly what they sound like. They're just called unit vectors. They have a magnitude of 1, and they're at 0, 1, and 1, 0. And then when we get to 3 space, so this is later on in the course, when we get to 3 space, we'll add in a k vector, which will be on our z-axis, and it will have a magnitude of 1. So in 3 space, our k unit vector will be at 0, 0, 1. So it'll be on the z-axis. Okay, so let's just say something weird about this stuff. Okay, here we go. Let's try this. So we've got the origin, and then we've got some vector, some point A out here, and some point B over here. And then we've got this point P at coordinates AB. And we're going to call this vector U and give it the coordinates of AB. Okay, so if we wanted to represent this as a unit vector, we could do it. So bear with me here, but if we wanted to say vector U, we could actually call it, we could actually say I hat plus B j hat. Or vector I, vector B, however you want to say it. So we could actually represent that vector by writing it like this. And the reason we could do that is because we know that actually vector I is just the vector 1, 0, and vector B is just the vector 0, 1. Or another way to write it is we could say we know that well, I guess I'm just going to say, like, we know vector A is, if you split up into components, that's like A0. And this vector over here is like 0B, right? If we're representing this point on the line, we would call it like A0. And then we also know that this vector is 1, 0. We know that this unit vector is 0, 1. So yeah, I don't know. Just another way to say that. So I guess, I don't know, this is just preparing for the next thing we're going to do here. So I guess we can represent U in terms of its components. So we can represent U as saying like A0 plus 0B. So we're just breaking vector U up into its x component, so which is at A0, and then its y component, which would be at 0B. And then we're saying that, well, if we added our x coordinates, we'd get A, and if we added our y coordinates, we'd just get B. So any vector can be written as the sum of its vertical and horizontal components. So you know how we normally write vectors like 3, 1, for example. Well, that vector could be written as 3, 0 plus 0, 1. So we could write these in terms of their x and y components on a grid. That's all I'm getting at in a confusing way. Okay, so that brings us to, we kind of already covered it, adding Cartesian vectors. So if we want to add Cartesian vectors together, then we just do it this way. So let's say we have vector U, and let's say we have U1 and U2 for the x and y coordinate. And then we have another vector V, and let's say we represent that as V1 and V2. If we wanted to add vector U plus vector V together, let me just write that out. So it'd be like adding vector U plus vector V, like that. Here's how we could like kind of, I guess, prove how we add vectors together. So this is just like a little proof, I guess, and I'm going to use unit vectors to do it. So first let me split this up into components. So if I wanted to represent this, I could write that as u1, 0, plus I could write this guy as 0, u2, plus I could represent this guy as v1, 0, and then the next one as 0, v2. So I could split it up like that. So I've kind of split it up into like, components, but then I'm going to add like a unit vector component to this. So then next thing I know is that, I know that the unit vector for this is just like 1, 0. So I could write that as u1 I hat. So that's like just a thing here. u1 comma like bracket 1, 0, which if you just distributed that, it would be like u1, 0, just what we have. So that's all that's saying. It's just like we're writing it using in terms of like a unit vector. So then this one would be u2 j hat, because the j unit vector is 0, 1. So that would work. Plus, we could represent the next one as v1 I hat, and then v2 j hat. So we could write them all in terms of unit vectors. And then I could factor out the i's. So I've got this one and this one. So I could group those two together. So I could have u1 plus v1. And then I've just factored out I hat. And then I could add that to, I could have u2 plus v2. And I could factor out j hat. And then just keeping going, I could change the I hat and j hat into their unit vectors. So I could change that into 1, 0. And then I could change the other one into 0, 1. And then I could just distribute that. So I would basically have, one sec here, I would have u1 plus v1 comma 0. Because if I just distributed, like multiplied all this by 1 for the x coordinate, and then multiplied it by 0 for the y coordinate, that's what I would get. And then the next one, I would get 0, since this is 0. And then I would get u2 plus v2 if I just like distributed that unit vector through it. And then, next step, all I've done is just like in the previous thing where we ended up writing a vector in terms of its components. So now you can see that that's what's happening here. So our x component is just u1 plus v1, and our y component is just u2 plus v2. So what that does is we've just proved that if we wanted to add two vectors together, u plus v, we just kind of went through a proof that shows we just can add the x components and the y's together. And that's how we could add Cartesian vectors. So you don't ever have to do it like this again. It's just showing you that if you had a vector A that was 1, 2, and a vector B that was -3, 4, and you wanted to add A plus B together, it's just showing that you have to add their x components together. So 1 plus -3. And then you have to add their y components, so 2 plus 4. So vector A plus vector B would be equal to -2, 6. So it's just showing us how to add vectors. That was just like a little proof on how you add Cartesian vectors together. So it's just as simple as that. You're just adding their x components together, and then you're adding their y components together. So adding Cartesian vectors is like way easier than adding geometric ones. Okay. So let's just try a couple questions. So let's say we had vector A is equal to 5, -7. And let's say we had vector B is equal to 2, 3. Okay, so what if we wanted to add the two vectors together? Let's try that. So we learned all we do is add the x component. So 5 plus 2 would be 7. And we just add the y component. So negative 7 plus 3 would be negative 4. Boom. That's how we add vectors. What if we wanted to multiply a vector by a scalar? So 3 times vector A. So we learned that all we have to do is multiply that 3 through the vector. So 15, negative 21. And now this vector, 15, negative 21, would be collinear to vector A. Okay, what if we wanted to subtract vectors? What if we wanted to do like 2A minus 4B? So if we wanted to do something like that, so 2 times vector A minus 4 times vector B. So first thing we have to do is do our scalar multiplication. So you have 10, negative 14. And then the next part we have to do is 8, 12. And then we just subtract our x's. So 10 minus 8 would be 2. And negative 14 minus 12 would be negative 26. So that's how you subtract vectors and multiply them by scalars. You could also express vectors in terms of unit vectors. So let's say we wanted to express vector b in terms of I hat and j hat. So say we wanted to do that. So vector b is 2, 3. So we can just express that as 2 I hat plus 3 j hat. And if you're not really sure, like, whoa, why'd that happen? Why is there a plus there all of a sudden? That is the answer. But just to show you what that means, it means 2 times vector 1, 0 plus 3 times vector 0, 1, which would mean 2, 0 plus 0, 3. And if we add those vectors together, we would get 2, 3, which is what vector b is. So this is how you write things in terms of unit vectors. And I guess that's it.